Hey, well, good morning, everybody. Thanks for joining us today. My name is Valentin Troll, and my contact details are there. I'm the head of the Natural Resources and Sustainable Development section, and I am a geologist by training, and I've been working with resources for a little while, but I also work a lot with natural hazards, and there is a link between the two, because natural hazards, they have an impact on how we use resources. But today I'd like to focus on mining in particular and resources. Should we switch the light off? You might be able to see the slides a little better. Is that okay? That work for everybody? Okay, great. So today I'd like to talk for the first hour of our session about resources, mineral and metal resources. And then I'd like to touch on mining and all the problems that come with mining. And afterwards, we're going to have a short break, and then we were sent some video clips. I'd like to show them again today, and then I'd love to have a little discussion with you guys about how you feel, what you think, and whether there's any way forward, at least from your perspective. So let's start with a few basic concepts, and that is the use of metals and minerals, the use of resources. And the truth is that every one of us uses, on average, about 1.4 million kilograms of metal or mineral resources over your lifetime. Here's a little split up of all the things, and I don't want to necessarily go into details, but you as an average person, you're using 400 kilograms of copper every lifetime. So 350 kilograms of lead, 330 kilograms of zinc, and it goes on and on. You use 30 grams of gold. Gold is very rare, obviously. And the things you use the most, or we use the most, is actually aggregates, sand, stone, gravel. We use it everywhere. We put it in concrete, we put it into tarmac on the roads, we use it to fill kind of things, and we're using literally hundreds of thousands of kilos per person every lifetime. So the amount of material we use is actually quite staggering if you think about it. And let's see. Here we are. So here's all the different things, and some of these terms may be familiar to you, others not, but we're using all these things the environment provides for our society. And here's some kind of certain minerals like zeolites and halite. Zeolites is a white little mineral and has really great properties for filtering water, for example. And then halite is just simple salt, but we also use beryllium. This is a source for certain elements. And of course, graphite, things like that. So this is mainly minerals, but we also use metals a lot. And here's a few metals like tungsten, and here's lead and lithium and nickel, for example, and we use them to aggregate different things. We are building things from that, and that is, of course, where the demand comes in. Here's just a few examples. So if you think about where you live, you have dry walls. They're made of gypsum. We have to mine it. And then concrete. Well, in order to make concrete, you actually need rock material. You mine limestone for that because it binds afterwards again. If you want to make bricks, you need clay. You have to mine the clay. And if you want to make paint, you need certain elements for that. So if you want to make windows, you need silica to make glass. And if you want to have any kind of electronics, you usually require a good bit of copper for that. Iron is the most important metal we are mining. There's a lot of talk about rare earth elements these days, but the metal that is the, industrially speaking, the most important one is iron. We are using vast amounts of iron, more than any other metal. When you think of building a bridge, building a car, building steel reinforced concrete tower or something like this, then all of these things require that we mine iron. Actually, I should stress right now, the EU, with all the discussion, we are still importing iron from Russia because we're not mining enough in the EU, but I'll come back to that a little later. So we also need a lot of other metals, chromium, nickel, molybdenum, and things like that in order to improve the quality of the iron, improve the steel, for example, and we are making alloys out of them. Hey, good morning. So when we think about where do we find them, what is the distribution of these resources inside our planet, and we're talking mainly about the crust of the planet, only the upper part, then we find that there's actually a very small number of elements that make up the vast majority of the rocks, and these are the ones listed here. Believe it or not, actually the most abundant element in rocks is oxygen, because we're binding all these other components usually with oxygen. So silica is bound as SiO2. So we have two oxygen in a silica tetrahedron, and there we actually making a lot of these oxides. We need a lot of oxygen for that, but here's the important ones: magnesium, sodium, calcium, iron, etc., and titanium. And then we have a vast sway of other elements, and these are, of course, in the periodic table. Here's the atomic number set. So this is the rock-forming elements. These are these guys here. But then we have all of those, and they only make a tiny percentage. They make less than 1% of the entire Earth, and even of the Earth crust, and that's making them a little more rare. So the remaining 0.3%, they contain all these other things that we are so keen on. Gold is, of course, part of that. Rare earth elements are part of this. Diamonds, which is carbon, is part of this. Copper, platinum, for example, and they are all occurring at very low concentrations in the Earth crust. And that is the challenge. So we can subdivide them, I mentioned it earlier, into rocks and minerals and into metals. So I'm going to give you a little rundown of these different things now so that you have an overview. And when we think about minerals and rocks that we use in an industrial way, then, well, rocks have economic value. This is why we quarry and mine them. And they have different properties depending on the type of rock. And here's a few examples of what is mined in Sweden. We mine limestone, for example, on Gotland to make concrete, and also mix it with other things. And we're actually using it also for medical things. Graphite is something we use, and you know, when you have a pencil, you have graphite in there, but it's also useful for heat insulation, for batteries, etc. We can mine sandstone. There's a lot of quartz in there, and that's very important because we need the silica to make glass. So if you want to make window glass, you need to actually get the quartz from somewhere, and for that you usually use a quartz-rich sandstone, or quartzite, as some people call it. And then, for example, talc, it's a metamorphic mineral, and it's kind of making this kind of fine, slimy surface, and you can use it for lubrication and things like that. It's also used for glazing and in plastics and things like that. So all of these things are mined here, and there's a few more examples. So diamond, gypsum, garnet, clays, barite, corundum. Corundum is very good for abrasion, for example. Sulfur is very good for making dynamite. And dynamite can be used in various ways, obviously. And then we have pumice rock, for example, which is used as a building stone. It's also used as an abrasion. And sometimes, you know, you might have a pumice stone to kind of rub your feet. So all of this material comes from quarries. So, and if you light a match, for example, well, there's sulfur in there, and the sulfur comes from a mine. These days, we're also producing a lot of sulfur as a byproduct of the petroleum industry. And if we go off fossil fuels, we will actually have to go back and mining the sulfur again. And when you have the smell after a match, it's actually you're depositing tiny little flakes of sulfur on your match. So let's go and look at this now. So the development of our society is strongly dependent on the use of resources. So the anthroposphere, the human world, if you will, that has been forming over the last tens of thousands of years, we have increasingly used more resources. And we only learned to use metals a few thousand years ago. Prior to that, we were effectively in a stone age, and then people started to work out, oh, we can actually use metals. It's believed that it's accidental that we discovered the use of metals. Some people argue people found a meteorite and realized, oh, something is different, and they started to work it. The Inuit in Greenland, they mined meteorite metal that was on the ice sheets. So the Egyptians did that as well. But with time, people learned, oh, if you heat it up, if you smelt it, you can do things with it. And they have unique properties that are very useful. So we started off with effectively using stones. If you look at cultures like the Maori in New Zealand or Polynesian cultures on Hawaii, they had no metals. There is virtually no metal there. They lived in a Stone Age, in a forced Stone Age. Where there was access to this, the Bronze Age came about, where you start to use relatively soft metals, copper, tin, gold. You blend them, you make an alloy, and that can be used then. And then a little later, we started to work out how iron actually forms and how we can use it and how we can make it into tools. And that gave our society an enormous edge because we were suddenly able to make steel. And steel has very unique properties. And then eventually we also learned the tricks of making ceramics. And initially, of course, this came from China, and then the Europeans, after many failed attempts, learned to do that as well. And that had a huge impact on hygiene, for example. And then now in the industrial era, starting after the medieval times, we are starting to use more and more of these. And nowadays, over the last 50 to 70 years, we have learned to use rare earth elements, and there's an increasing use of those. So these metallic resources, well, as I said, they go back to ancient cultures. People have realized very quickly that gold has unique properties. It's chemically inert. It doesn't react with anything, and it's very rare. So people were very keen to get this. It's actually in extremely low concentration in the Earth crust, 4 parts per billion. So if you have a billion particles, 4 of them would be gold if you take the Earth crust as an average. So, and it's therefore extremely expensive, and many people also use it to preserve value. So, well, Fort Knox has these gold bars in order to make sure that we can maintain a certain financial standard even in crisis. We don't need to go into that. That's just giving you a feeling for how big and how little it is. So 1 ppm, 1 part per million, is just this tiny little thing here, and 1 part per billion is even less. So this would be the concentration of certain things within the entire crust, giving you a sense of how rare these things actually are. So metallic resources, copper is very important. Copper occurs in, well, copper deposits, and here's a typical copper mineral, chalcopyrite. It's a copper ore, and it occurs at about 100 parts per million. It's a lot more abundant than gold, but it's still pretty rare. So 25,000 times more common than gold in the Earth crust. And this is why people started to use copper early on, because it's comparatively easy to find, and it's comparatively easy to work. So economically, it's also therefore a lot cheaper. This is Chuquicamata, the largest copper mine in the world in the high Andes of Chile. And there, it's still a lot of copper mining going on, and there will be more probably in the future. So in Europe, we have been mining, well, since medieval times. In Sweden, there's recorded mines going back to well before 1000 AD. And here in the 4th millennium BC is the oldest mining record. And then, of course, this grew stronger and stronger. Eventually, mining was taken from, for example, Europe to South America, where the Spanish mined silver and copper and gold in the Andes, and it was actually financing the entire Spanish Empire at the time. So in the Earth crust, we have different concentrations of these, and here's just Cerro Rico, one of the mountains in, I think it's Bolivia, which was mined for silver and copper and eventually also gold. So if you think about the timeline there, gold is known for quite some time, and there's good evidence that this goes back to about 6000 BC. Copper is a little later, silver is about the same time, and if you mix copper and tin, for example, you get bronze. And this was what happened there. We started the Bronze Age by making simple tools and weapons, and this was actually a big step. Only much later did we learn to use iron and smelter iron, actually. So, and there We have a stone, people discover a stone, and then you start to potentially make I don't know, a campfire, and you realize when the campfire gets too hot, some of the stones start to melt. And then you realize the next morning, oh, this is very different. And I think it was accidental that we learned this. But once people understood what this means, we were actually able to work with it. So only relatively recently have we used other metals like aluminium. Aluminium is very light, as you all know, and it's now almost everywhere. You are touching aluminium multiple times a day, and it's ductile, it's good in terms of corrosion resistance, and it's also electrically very conducting. So we use this as wrap, and in tin cans, we call them tin cans, but it's actually aluminium. And then most of these products have an element of aluminium in there. So metals occur in ore deposits, and ore deposits is a high concentration of certain metals. And this is, of course, what geologists want to find, and this is what sponsors want to find. Because these things are so rare, you need a unique situation where this is concentrated. And this is a sample from South Africa. This is actually a gold, from a gold deposit. And there you see the tiny little gold flakes. This is really highly concentrated. So if you find this on your land, you're rich. But yeah, if you kind of want to find this, you're sending out geologists, prospectors to find this kind of thing. And then once you find it, then all the other processes start. Can you actually mine it? Who owns it? What is the conditions? How far is it? Etc., etc. We'll come back to that a little later. But before we go there, I'd like to talk a little bit about rare earth elements. This is a big thing. This is now coming stronger and stronger for the last about 2 decades. Rare earth elements is what we need increasingly for the electronic market, but also for the green transition. Why is that? Well, they have unique properties. And the rare earth elements, for those who are chemically not so into periodic tables and things like that, let me point out, rare earth elements are mainly these guys here, the lanthanides, from lanthanum to ytterbium. And there we have a lot of very awkward kind of little metals with very low concentrations. Many of them were found in various parts of the world. In fact, Sweden actually gave name to most of the rare earth elements on the planet. So here we have holmium, and we have gadolinium, and we have dysprosium, and etc. And ytterbium and ytterbium, and here's ytterbium. And this comes from this place near Stockholm, Ytterby. And this actually was the place where many of them were initially found or separated, and therefore many of the rare earth elements are actually named after Swedish places. So, having said this, let's have a little look at this in more detail. So here is a few rare earth minerals. I don't need you to understand necessarily how they come about or what these formulae are, but I'd like you to have a rough idea that you've seen them. So there's various rare minerals that contain them. So here we have monazite, which has a lot of cerium and lanthanum. Here we have apatite. This is also what they have as a byproduct in Kiruna. And there we have a lot of fluorite and phosphorus, but also it carries rare earth. Xenotime here has yttrium, and here titanite has, of course, titanium, and commonly also substituting into that is a lot of rare earth. Here we have cerium, yttrium, lanthanum, and alunite, for example. So these are rare minerals, and if you find them in large quantities, you can try to extract these elements from there. So prior to the 60s, we hadn't really much use for rare earth elements because technologically, we really didn't know what to do with them. But this has changed now over the last few decades. And now we're actually going back to the old spoil heaps in Sweden, because what was mined in the Middle Ages was basically copper and iron. Nobody cared about rare earth. And now we are going back to trying to find whether people have thrown away the things that we now value. And actually, there is good indication that many of the old spoils contain quite a lot of it. However, right now, most of the rare earths come from China. China has a complete domination of the rare earth market and produces over 90% of all the rare earth that we use. So if you have a mobile phone, there's rare earth elements in there, and they are absolutely most certainly from China. So the demand currently continues to rise. It's skyrocketing, in fact. So there will be a lot more rare earth needed given projections of our current industrial activities. So China, as I said, it's the dominant force on the market for rare earth, and it can actually restrict exports. It did so a while back. They are not the friendliest with Japan, and they actually stopped exporting to Japan for some time. And the Japanese got really greedy. They started to stockpile rare earth for feeding their economy for at least 6 months. So there is now a bit of a rare earth kind of tension building up, and it might actually get worse in the future. There is rare earth, of course, in other places of the world. Here's Mountain Pass. It's a big rare earth mine in California. And now the Australians are starting to explore for rare earth. And we also have some potential deposits in Sweden. And there's one in Norra Kärr. But the public resistance to mining was so strong that all attempts to mine rare earth in Sweden have actually been halted now. And we'll come back to that a little later. So the US has a large consumption, and the US being representative of the Western world. So here we are actually producing far too little for what we are consuming, and consumer demands are growing enormously. So it's not only in smartphones, it's also in medical and green tech. So there's a lot of rare earth going into, for example, wind turbines and, well, electric cars and things like that. So where do they come from right now? They come from this place in Mongolia, and it's part of China. And Bayan Obo is the big mine, and it's very easy to mine there. It's close to the surface, so they don't have to dig deep, which is a difference to, for example, Swedish deposits. You might need to go deeper, making it more expensive. They can really just pick it up from the surface. Conditions are quite, the Chinese are not very good at revealing what's going on, but conditions are, according to them, beautiful, but other reports say conditions are quite bad, and there is entire lakes that are now poisoned because of too high concentrations of rare earth. Apparently, safety for workers is also not very good. So you can argue this, but we're buying a lot of these metals at a reasonable price right now, and I don't think a lot of people care really how they come about and what the conditions are under which they are mined. So here is a little kind of diagram. This gives you the demand over time going back to the 1950s. And here in the 1980s, so this is when I was born, there was no market for rare earth. Nobody cared. So, but since then, this has changed dramatically. And you see in red, we have China. It's taken over the entire market, and by now China produces virtually all the rare earth we have and we use. So the demand is growing, and here's just a few examples. If you think about an electric car, and it doesn't matter which brand, it's the same thing for every brand. There we use different rare earth elements for different things. So if you look at certain sensors, they require yttrium. The LCD screen needs europium, yttrium, and cerium. Even the glass in cars has special properties. It needs certain kind of elements. And when you think of the battery and the electric kind of engine there we need neodymium, praseodymium, dysprosium, terbium, all of them very rare elements, and they need to come from somewhere. So the mobile phones is an issue. Everybody uses them. Lighting is an issue. All of them use different ones. The colors on the display of your mobile phone is the same problem as in the car. They actually require certain rare earth elements. And again, I don't want to kind of dull you with too many details, but you can look this up. Here is what goes into your smartphone. And there's, of course, elements that are plentiful, like aluminium and potassium. That's easy. But when it comes to indium, for example, neodymium, praseodymium, dysprosium, these are not things that we mine in Europe right now. They come from elsewhere. They are imported at, well, long distance travel and at prices that we don't necessarily make and at conditions that we not necessarily control. So when you think about green technology, then a lot of rare earth goes into that. So one of these kind of towers, wind towers, needs 26,000 kilograms of steel and 190 cubic meters of concrete. So it's a lot of material going into these things, and the actual turbines, they need rare earth as well at reasonably high concentrations, in fact. So the highest supply risks is indeed for rare earth elements, and there's various kind of social media things here. Geoscientists and people who work in the industry, they realize these problems, but a lot of people, I don't think, are aware of these kind of issues. And electric cars and smartphones are creating a huge demand for these. You can plot this up, actually. So here is a diagram. This is the economic importance on this side. Here's the supply risk. So I said earlier that iron is something we need loads of, and it's very important. So the economic importance is very high. But good thing is we have loads of iron. So the north of Sweden has plenty of iron. They would like to mine more iron because we're still importing from Russia. And of course, we'd like to reduce our external dependency, but there's no real issue. We have iron for the next hundreds of years, even here in Sweden. But when you think of the opposite, this is light and heavy rare earth elements. They're economically increasingly important. They're shifting more and more to the right, but we have a huge supply risk because we are not mining them here. They're coming from elsewhere. We are dependent on the supplier. Some people even liken it to a drug addict. Some people say Europe and the Western world is like addicted to these things, and we have to buy from whoever the dealer is at any price they're making. And this, of course, puts us geopolitically into a very awkward situation. And this is why the EU has offered directives now to find more in Sweden. And I'll say a few words about this later. We're actually doing very badly at that. That's the downside of it. So once the technical side is sorted, I'll show you a map of Sweden now. And Sweden has been a mining country, a traditional mining country for a long time. Thank you so much, Monica. And here's the geology of Sweden. We have the Fennoscandian Shield. This is the orange part here. That's very, very old rocks. These other rocks are a lot younger. And there's a lot of metals in the old rocks. When the earth was young, things were obviously a little different. We concentrated a lot of metals in that. This is a volcanic area. So there was a big volcanic, situation there back in the days 1.9 giga years ago, and many of the metals come with volcanoes. It's believed that the situation in Sweden 1.9 giga years ago was a bit like what we see in the Andes today. Many volcanoes, but also many ore deposits. And now all the volcanoes are gone. They're stripped away by erosion, and that means we have easy access to many of those metals. This is why Sweden has been attractive as a mining country for quite some time. So here's some of the biggest deposits in Sweden, and depending on what you mine, there's different concentrations of that. This is the traditional mining area here in Bergslagen, and we are somewhere here. So it's very close to us, in fact. And there we have another big mining area in the north of Sweden. This is where Kiruna is located, but also other places like Malmberget, which is the second biggest iron mine. And then there's various other ones that also mine, for example, copper and things like that. So Kiruna is very young. It was only really opened 100 years ago. But when we think of Falun, for example, or Garpenberg, there's evidence that this has been mined well before the Middle Ages. And they are still in places mined today. So some of these mining activities go on. It would have started as artisanal mining, meaning very small family kind of businesses, and maybe even that a farmer at the same time in winter would do a bit of smeltering to make some tools, and then it would go further and further and become increasingly industrialized. By the early kind of modern times, Sala, for example, was open. Sala was the source of silver. The Swedish Stormax team, it was actually almost entirely financed from that single mine, Sala, the silver mine. And here, Grängesberg is a big iron mine that that's just about here. And it was closed in the 80s, mainly because of geopolitical reasons. And now there's discussion, should we reopen it? Because there's still a lot of metal in there. So having given you a rough idea of this, so this is a projection of how much is there. And geologists talk about reserves and resources. There's a mild difference. We don't need to go into the details here. But one is, how much do we know that we have and how much is actually there? So there's a mild difference. Even when it's there, we might not be able to get it. So that defines the difference here. But when we look at the reserves here, millions of tons, this is really where Sweden's capital lies. There's huge amounts of metals up there in the north. And this is, of course, where a lot of mining activity is currently centered. Now, mining is not a very pleasant business. We all know that. Nobody makes a secret of that. So mining comes with a lot of side effects, and if you don't take care of things, you're making a real mess. And in many parts of the world where mining is not regulated, this is actually what's happening. We have water pollution, for example. This affects not only the local system with acid mine drainage, it really goes on further and further, and it continues when you process the metals, when you, for example, use arsenic to leach gold out of rocks. If you don't do this in a closed system, in a controlled way, you're liberating arsenic into the environment, and you can work out what happens there. It's not very healthy for you. And this is very common. This is a big mine, I think, in South Africa. So there's big holes in the ground, and mining can also cause underground instability. We know that Kiruna is actually sinking right now, and they have to resettle the town. The people in Kiruna don't mind because actually 90% of them work for the mining company. They wouldn't be there without this. So, but these are side effects. These are negative consequences that come from mining. And therefore, these mining activities often experience a lot of resistance. So there is a lot of public opposition to mining. And here's just a few impressions from various kind of parts of the world. So mining is not universally popular. And people kind of have this slogan, it's called NIMBY. NIMBY means not in my backyard. So people don't want to be close to mines. There has been a huge lithium mine project in Portugal, which is now shut down. There's been one in Serbia, which has now been shut down. So it's not that we don't have these metals, it's that a lot of people actually don't want the mining. And this, of course, comes with all sorts of kind of side effects again. So here you can say no to the mine, but then where do you get all the metals from for the energy transition? And well, you have to buy them elsewhere if you don't want mining in your backyard. So, and this is part of the issue here. Here we have the global production of non-ferrous metals, i.e. metals that are not iron. And you can see that here we have Europe. Europe is rather kind of stagnant here in terms of the production for the last 30, 40 years, while North America is also kind of stagnant. Asia is really rising. We are buying a lot of metals from Asia. Well, I told you China is 95% of the rare earth market. This is also in this part here. So a lot of it is mined elsewhere, while a lot of it is consumed here in the European Union. And this is from a little paper I wrote together with a colleague a few years ago, and I think I sent it to your colleague for distribution. This is EU import, and therefore the reliance, the EU's reliance on these kind of imports. And well, we are importing a lot of material. We are importing 100% of all of these, including the rare earth. We are not actually producing them here. And there we have also rubber, for example, but that's not a metal, of course, but it was part of this, so we thought we'd leave it in. But when we think of all of these other metals, we're still importing 82% of copper. Can you believe it? Bauxite is the ore we need for aluminium. 85% of bauxite is not coming from the EU. And then we have elements like cobalt. Cobalt is vital for making batteries. If you drive a Tesla, you have cobalt in there. And I tell you, 65% of the cobalt actually comes from one place. It's the Democratic Republic of Congo. If you drive a Tesla, you have cobalt from Congo in there. There's no question about this. So these are kind of our realities that we need to deal with. Now, A lot of people come and say, well, we could recycle once we have mined enough. And I go, yes, in theory we can. But for most of those things, we actually have no means of recycling yet. So lithium, for example, we need lithium for batteries. Here, the full color is what we mine in the EU. The dashed one is what we can recycle. And this is what we have to import. So looking at iron, we're mining a lot of iron in the EU, but we still have to import a lot. And we can recycle because we can resmelt it. It's okay. We're getting better at it, so that's promising. Copper. We are mining a lot in the EU. We also have to import a fair bit, and we have worked out how to recycle it. Aluminium is similar. Tin. We actually have no bar for recycling here. Same for lithium. We have neither the technology nor the know-how to actually recycle any of this at this present day and age. Platinum, we can recycle a little bit, but most of it we actually have to mine, and most of it is mined outside the EU. So while the idea is wonderful to recycle it, we don't have enough metal in the system to recycle, and we don't know how to do it yet. It'll be decades before we will actually be able to start to recycle lithium. Once the first Teslas go out of use, then there will be probably Tesla heaps and battery heaps, and we have to start using that. Again, we are a bit slow. The Chinese are a lot better, and most of the lithium refinement is actually happening in China, and most likely most of the lithium recycling will be happening in China. It's a bit like our electronics. Most of our electro rubbish is actually shipped to China, and they are getting the copper out and the other kind of elements. We in the EU, we're not doing this very well. And it's exemplified with this next map here. So this is on the left hand, ore deposits in Europe. And this is just really Western Europe and North and South as well. And you see it's dotted. We have a lot of ore deposits in Europe. But these ones are the ones that are actually mined, or whether there is actually exploration. Exploration doesn't even mean mining. We're just looking for things. And you see, Sweden is actually having a lot of exploration compared to other things. Ireland is also a geochemical anomaly. It has a lot of ore deposits. Portugal as well. And the rocks in Spain are the same, but the Spanish hate the mining. So you see there's a huge difference here just on this small scale. The French are really opposed to mining, and you see there's virtually no exploration. And then, for example, the Austrians, they like mining. It's an old tradition there, so they have some activity. So there's a huge discrepancy in what we have and what we want to use right now, and this is a big problem. Let me bring you back to Swedish kind of situation right now. Here we have applications for exploration permits in Sweden. There was this huge spike after the EU released the doctrine that we should find these metals more in the EU homeland rather than importing it. And there was a lot more exploration permits, but many of these exploration permits that led to discoveries did not lead to mining. There's a huge way from exploring it to finding it to actually getting everything right and then starting to mine it. And many companies are actually leaving now. There was this big story of Scan Vanadium, a big company. They wanted to mine vanadium in Skåne, and they got so much resistance that they now moved out. They just bought a mine in Africa. So, and it's cheaper, it's easier. Given that we have these huge demands, I think I can, understand why they're doing that. Is this morally correct? That's a different discussion. But I think economically, I can see why companies would be tempted. Let me give you a flavor of this. A conventional car, this is an American slide. So this is why they have pounds here. And a conventional car needs maximum about 50 pounds of copper. If you want to kind of think about hybrid vehicles, you're up to 85. Plug-in 130. Battery, kind of pure battery ones, not hybrid, 180. If you think about making larger vehicles into electric vehicles like buses or so, 190, 200 almost. If you think of a fully Tesla-style bus, you would need 800 pounds of copper. You see the demand for it is exponential. And here's just something I clipped from social media. This chap here is discussing this. We don't need to go into numbers. The takeaway point is that this guy argues most people have no idea about the vastness of metals that will be required in order to actually see the energy transition to come about. So here is the whole thing as a bar chart here for transport. A conventional car needs not a lot of metal, comparatively speaking, while an electric car needs a huge range of metals and a lot of it. So this includes the rare earth, for example. And when we think of power generation, offshore wind needs huge amounts of metals. Onshore wind, a little less, but still a lot. Solar panels, they require quite a lot. If you think of coal and gas and nuclear, they all need a lot less mining. And this is why these things have been so attractive in the past. In the Industrial Revolution, well, you have loads of coal, for example, and increasingly we also explored gas for an energy source, but they don't need a lot of infrastructure. We can use it in a simple way, while these things demand vast amounts of mining to happen in the future. So here's some projections, and this is from the literature. Again, we don't need to go into details, but the red areas on those graphs are projected demands. The little black lines is the current situation. If you look at neodymium, one of those elements we discussed, one of those rare earth elements, the blue dots are what we need for kind of low carbon technology, and the other uses are part of the red dot suite. And so we're spanning up this field, and projections are uncertain, of course. There is a huge error margin, but when we think of what we potentially might need, it's vast. And then, of course, we're looking at other elements, dysprosium, platinum, indium, etc. Even silver, we will need a lot more. So effectively, what some people argue is we will have to mine more than what all humans have ever mined on this planet before. Vastly more in order to facilitate the energy transition. So the problems that come with there is that in Europe, there is big regulations, and this is partly the problem why companies move away, because you have public opposition and you are pinned down by the government. You have to follow certain environmental regulations. You have to have all sorts of plans of how to recreate the sites after you have mined it and things like that. While in many other parts of the world, there is no such thing. So, I mean, China, etc., Africa, we have these wastelands from mining, and these, of course, they paint a very bad picture. And sadly, this is a reality in many parts of the world. So, and this leads on to this current discussion. Where should we mine? Because if we accept that we need it, but we don't want the mining here, we're accepting that mining will take place elsewhere. And that is a real mess, because if you drive a Tesla, there is no way that you can avoid the moral issue that you have child labor cobalt in your Tesla. This is the bitter reality. It's so bad that they have now measured that there is DNA changes in kids that work in the mines in Congo. So because it's so unhealthy. Usually mining is organized, but about 20% of the cobalt comes from artisanal mining, meaning family business. They don't care about how the mine site looks afterwards. They don't have an education in how to stabilize mine shafts. They don't care about what the water does, and I don't blame them. I'm just saying this is problems that come with that. If you look at videos of mining in, for example, Congo, it is quite disturbing, to be honest, but we're quite happy to do that because it's out of sight. So if you say not in my backyard, you're morally accepting this. And here's a few more impressions. So the thing is that for those people there, a child laborer in Congo actually earns a lot more money than a farm laborer. So it's attractive even for the kids to go there. So it's a strange kind of situation. So going there and saying we shouldn't have child labor is also very tricky, because you're actually undermining many of the family's income sources. So it's a wicked problem, as I call it, because there's no simple answer to this. What are the alternatives? One alternative is we could try to get cobalt, for example, from the ocean floor. There's a lot of ocean floor cobalt. given the demands we are projecting. Here we have a timeline again. This is to 2030. This is our current production of cobalt. This is what we will need. We're actually falling onto a 150,000 ton deficit there. And this means we now need to do something. The Dutch government has last year given green light for a large exploration project on the ocean floor. But this is a Greenpeace kind of cartoon. And it resonates with me quite strongly because here, the question is, what are we using these minerals for from the ocean floor? And the answer is to create clean technology. But of course, the irony is that in order to create this green technology, we are destroying other habitats, ecosystems, etc., etc. Now, some people argue, why not go somewhere completely different, where there is no life, where there is no issues, where there is no such thing, where we can't really spoil the environment? Well, where would that place be? Well, space mining. So the rocks with the highest concentration of cobalt are actually asteroids and planet cores. We can't go to our core, but we can look at broken up old planets. And there we actually have these metal lumps floating around in the asteroid belt. And some people say, maybe we can just go there and get them. The Japanese have just actually had a probe going to one of the asteroids and they took samples there. So technically it seems to be possible. And to make batteries, you need loads of cobalt. This is actually why Elon Musk has this space exploration company, because he knows there is a lot of cobalt in these kind of things. Now, there's other voices that say we messed up this planet, we shouldn't mess up other planets. On the other side, there's for sure no life that we recognize on any of those kind of asteroids. So is mining of asteroids an alternative? I don't know. It's not for me to answer, but we can discuss it. But the long and short of this is that in order to facilitate the green transition, in order to actually comply with these sustainable development goals, the amount of mining that we need to do is staggering. And how and where we do that, that's the challenges for the next few decades.